Hello, welcome to your next lesson on magnetic fields. Today we are looking at electromagnetic induction. So, if you can please type in the date, that would be fabulous. It's obviously not the 15th November 2017, so whatever today's date is. So, just to recap what we've done already, we've looked at the motor effect, and we've looked at Fleming's left-hand rule. And Fleming's left-hand rule is where you have a magnetic field and you put a current into it, and that causes something to move. So in terms of Fleming's left-hand rule, you're putting in two of the components, the field and the current, and you're creating movement. Now today, in electromagnetic induction, we're going to be putting in the movement. So we're going to be physically moving something, and we're going to be doing that in a magnetic field. And we'll be creating current. So this time we're putting in movement and field and we're getting current out. So we're still looking at the same three things, but this time we're inputting a different two and getting current out. So electromagnetic induction is creating electricity in a wire. So this is actually how every bit of electricity effectively that you use from a plug socket is created. We move a magnet inside a coil, and that creates a potential difference, remember that's another word for voltage, and current. Now I've used a key word here, which is induced. They really like the word induced. It means to create or produce, but they love that word induce. So sometimes in a mark scheme, if you have used the word induced, that would literally be a tick, as in, great, you've used the right word. So try and use the word induced rather than created or made. So if a magnet is moved inside a coil, potential difference and electric current is induced. This is because the magnetic field around the coil is changing. And in brackets, again, I've put a key phrase. Now, it very much frustrates me in this spec that they've put in this phrase, but they don't really expect you to understand it. They just expect you to use it. So the phrase is, the coil cuts through the lines of the field. Now, that's the phrase they want you to use. And again, if you are asked in an exam, why is electricity created, or why is it induced, should I say, then you should use that phrase. The coil cuts through the lines of the field, or the magnet cuts it, or whatever. But what it actually means is that when you are moving a magnet into a coil, the magnetic field around that magnet effectively goes through the coil. And the coil is going through all the different field lines. If you leave a magnet inside the coil, the field lines stay where they are, and the coil no longer cuts through any of them. They're not moving through each other. So no current will be created. You will only be creating current when there is movement. So you'll create a current when you go in, but then if you leave it there, nothing will happen. You'll also create a current when you pull the magnet out, but again, if you then left it out, nothing would happen. So it's all about that movement, that cutting through of field lines. Now, if you can please have a little look at the diagram on the right. I know it's a pain, but if you could try and draw that, that would be fabulous. You have a coil with a magnet being pushed inside at the top, and you can see that a current is being created. That's like a little ammeter, just trying to show you that a current is being created in a certain direction. Now have a look at the diagram on the bottom and compare it. This time the magnet is being pulled out. And can you see that the current is going in the opposite direction? So if you push a magnet inside, it will create a current going one way. And when you pull it out again, it will create a current going in the opposite direction. And that's actually really important. So the next thing we are going to look at is how to get current increased. So if we're going to be using it from our plug sockets, we need a fair amount of current and potential difference. So how do we increase it? And we can do that by increasing the number of coils on that coil that you're using, increasing the speed at which the magnet coil moves, so the faster you're going in and out, the more current you'll create, and increasing the strength of the magnet, because then there'll be more field lines for that coil to cut through. Now, a generator, which we will go into more detail in another lesson, is something that creates electricity and it does it continuously, so that you can actually use it, as opposed to just having a little spike, a little spike. So here can you see in that diagram, you've got someone rotating a coil. So they are putting the movement in because there is that physical rotation. They're putting the movement in. That's just a coil. There is no power source. They are just bits of wire. So they're rotating a bit of wire in a magnetic field and they're getting current out. Now it is really, really important that you're very clear that in electromagnetic induction, you put movement in and magnetic field in. You do not put the current in. That's what you get out. That is our output. People get very confused between the motor effect and this. In the motor effect, you put current and magnetic field in and you get movement out. In this, you put movement and magnetic field in and you get current out. So they are very different. So a generator works by rotating a coil in a magnetic field and it produces alternating current, which is current that goes backwards and forwards. So I've put two examples of alternating current at the bottom there. You can see the, can I draw on this? I hope I can. Right. Yes, there you go. Wherever the current is positive, so above the line, that means the electrons will be flowing in one direction. Wherever it is below the line, the electrons will be flowing backwards in the opposite direction. So you can see in the one on the left here, they're going forwards, backwards, etc. Now have a look at the diagram on the right here. You can see they are changing much more quickly, backwards, forwards, etc. Not only that, but they're actually going faster. So I can tell that because the spikes are higher. So when I rotate a generator more quickly, I get more voltage or current out and it changes direction quicker. Now the next and last thing we're going to look at is a little bit weird. It's all about how to tell which direction the current that we are creating will be generated. So we know that if you push it one way, it'll create current one way. And if you pull it a magnet the other way, you'll create a current in the opposite direction. But how can you predict which way round it's going to be? So when a current flows through a wire, it creates a magnetic field. We know this already. We've looked at it. But if we are creating that magnetic field and that current by pushing a magnet into it, the field that will be created in your coil will try and stop you from doing what you are doing. Now I know that's a bit weird. So I want you to have a look at the diagrams on the right-hand side. At the top one, you have a south pole of a magnet being pushed into a coil. And can you see that the coil creates its own magnetic field and it creates a south pole? Now, why does it create a south pole? That is because it tries to stop you from pushing the magnet in. And we know that two south poles will repel each other. So if you try and push a south pole in, it will create a south pole to try and stop you. If you pull a south pole away, which is the bottom diagram, it will create a north pole to try and stop you, because this time it's trying to attract you back. So if you're pulling a south pole away, it will create a north pole to try and attract you back. So I'm just going to quickly draw a couple of diagrams and see if you can guess which way the current, the magnetic field will be created. So here's my coil. Oh, I did not leave myself enough space here. Anyway, right, north pole. If a north pole is going in, what magnetic field will be created at the end of that coil? Have a little think. Okay, if a north pole is going in, the coil will try and repel you and stop you from moving the coil in, which means it will create another north pole. If you are moving a north pole away, what magnetic pole, should I say, do you think the coil will create? It will create a south pole, and the way I know that is that it's going to try and attract you and try and stop you from moving that north pole away. So I'm hoping that makes sense. There is a little bit more, no, I'm not going to do it. We'll save it for another lesson. But yes, I hope that all made sense. Please let me know if you have any issues. I am hovering over my iPad and I shall see you all soon. Thank you.